All, welcome my friends. Now today I am planning to talk about analytic functions. So in my last lecture I talked about I introduced the notions of differentiability. Then I discussed that if I have a functions from C to C and if my function is complex differentiable, then necessary and sufficient conditions, and then I talked about Cauchy-Riemann equations. Then I am saying then I already discussed that if I have a functions complex valued functions and suppose it is of the form f is equal to u plus iv, and suppose u and v are not satisfying Cauchy-Riemann equations, then you can say that this my functions f is not complex differentiable. Then I raise a question that okay, now in case suppose they are satisfying a Cauchy-Riemann equations, still can I say that if my function is complex differentiable? Then there is a counter example I have discussed that yes, you have a functions f which is not complex differentiable, but I can write this functions f of the form u plus iv where u and v satisfies Cauchy-Riemann equations at that point, but still my function is not complex differentiable. So therefore the natural question, okay, if I have a functions suppose u and v satisfies Cauchy-Riemann equation, so that means I need to add something more on u and v so that I can talk about the complex differentiability, and that's how sufficient conditions I have discussed. And then I just briefly introduce the notions of analytic functions. So for today's lecture my kind of plan is that I should start with the definitions of analytic functions once again, and then I'll move forward couple of its properties, and then later I'll talk about harmonic functions and then how to calculate harmonic conjugate, and then I'll talk about what is called multi-valued functions and their branches. Yeah, so as I said, I should again start with the definitions of analytic functions, though I have discussed in my last lecture very briefly. Okay, so what is analytic functions? As I said, see, I have written analytic functions. So if I have a functions f, suppose this functions f defined on an open set, then first I am defining the notions of analytic functions in an open set. So this is I have written. Then the functions f is said to be analytic in an open set. So suppose you have a functions f defined on an open set S, and I am saying that my function is analytic on an open set S if my function is differentiable at each point on S. Okay. So one examples I have discussed, like the examples f of z is equal to z g of z is equal to z square. These are very nice functions, polynomial functions, they are analytic functions. However, f of z is equal to z bar we have already discussed, either using the principal definitions or using satisfying Cauchy-Riemann equations. This function is nowhere differentiable. G of z is equal to mod z square. This is also I already discussed that this function is differentiable only at the point 0, and it is except 0 it is nowhere differentiable in the complex plane. So therefore these functions are not analytic. And then I gave a definitions. What is the meaning of analytic functions at a point? So first I have defined the analytic functions on an open sets. Then I am saying that start with the functions f from some domain D subset of C to C, take a point z naught in D, and I am saying that my function is analytic at a point z naught if there exists a neighborhood which is an open set, right? Or you can think about open neighborhood, a neighborhood of z naught, and my function is analytic on that neighborhood. So though I am talking about analyticity at a point, but actually I am talking about analyticity on a neighborhood, on a or open neighborhood you can say. So that's exactly. So you see, so analytic at a point z naught if there exists an open neighborhood, so that I can talk about that my function is analytic on that open set. Okay, so even though I am talking about analyticity at a point, but actually I am talking about the analyticity on an open set, namely n of z naught around a point z naught. If this is the case, then I am saying that my function is analytic at the point, and if I say that my function is analytic in the full domain, then I am talking about that my function is analytic at each point. Then I raise a question, okay, so that this terminologies like analyticity, holomorphic or regularity, this kind of term, the same definitions will work, but the different book has different sort of notations. Like for example, if you go through the Conway books, I think they have the holomorphic functions. Okay. Then I raise a question that okay, suppose you have an analytic functions at a point z naught. Now question is, does it implies f is analytic in an open set containing z naught? And I already gave a hint that yes, this is indeed the case, because the difference between differentiability and analyticity is that analyticity like property is very rigid. Rigid means whenever I am talking about analyticity either say at a point or in some open set, that means I demand that my function should be differentiable at each point. Okay, but in a separate note you can think about or you can talk about the differentiability or complex differentiability at a single point, but the analyticity you cannot have it. It is a set property. This is a very rigid property. So okay, so therefore analyticity of a function is a set property, whereas differentiability is a point property. You can think about that. In that sense, analytic, if I say that my function is analytic, that means this function is very rigid. That means it's very concrete. And since I have a very rigid functions, you will see later on many nice properties will come out. And very nice theorem will be there if I have analytic functions. Okay, so that's what. So these questions you can think in this way. Suppose you have a point. Say this is my complex plane. So if I have a point z0, and suppose this is my neighborhood of z0, and at each point my function is differentiable, right? Though I am talking about it analytic at a point z0, but I am talking about the differentiability in a neighborhood of z0. That means n of z0. Now you see, since it is an open set around the point z0, so therefore if I take a nearby point here. So this point also inside this n of z0. So this point, if I talk about, if I already have the differentiability at each point in n of z0, so therefore I can also say that. So there is a if I take a nearby point, since n of z0 is an open set, so therefore there exists a small open neighborhood sitting inside this n of z0, and at each point my function is differentiable. That means what? That means even though I am saying that my function is analytic at a point z0, but it automatically implies that my function is analytic at a nearby point of z0 as well. So therefore, even though it is definition is saying that analytic at a point z0, but which automatically implies that my function is also analytic at the nearby point of z0, and so on and so forth. So if I go like that, and if I use the property that arbitrary union of open set is open, then you can easily kind of think, or you can easily convince by yourself that yes, that this is actually analyticity. Actually I am talking about differentiability on an open set or analytic on an open set. So that's exactly the question. So does it imply f is analytic in an open set containing z0? Answer is yes. Okay, because you just little perturb your point z0 to z1 and take a small open ball sitting inside, because n of z0 is an open set and my function is differentiable at each point. So therefore by definition of analyticity, this is also analytic at the nearby point. And if you go like that, and you can say that arbitrary union of open set is open, there you can conclude that yes, this is actually I am talking about analyticity in an open set containing z0. Okay, so couple of observations. So as I said, I already discussed, we emphasize that analyticity is a property defined over open sets. Okay, that's how I get the definitions. While, so look the comparisons, while the differentiability could conceivable hold at one point only. Okay, so therefore if I say that can you construct a function which is analytic exactly at one point at not other, it is not possible, because analyticity at a point will automatically implies that analyticity at a nearby point. However, you can have a function where my function is differentiable exactly at one point and it is nowhere differentiable. What kind of functions? I already discussed, g of z is equal to mod z square. This kind of functions, this function is differentiable exactly at the point 0, but it is nowhere differentiable in c minus 0, right? But you cannot have the kind of functions which is analytic exactly at one point, because analyticity is a set property. So that is, see I have written, that is we can have a function which is differentiable exactly at one point like these functions. However, we cannot construct a function which is analytic exactly at one point, because analyticity at one point, the way I have defined it, it automatically implies analyticity in a nearby point. In fact, analyticity on an open set. Okay, number 3, if we say that my function, okay, so now I have started with that. Okay, given a function shape defined on an open set, and if my function is differentiable at each point on that open set, then I am saying that my function is analytic on S, starting with an open set. Now you can say that, okay, if I start with some set which is not open, okay, if I say that fz is analytic on a set, I am not assuming that it is an open which is not open in C, then what is the meaning of analyticity on that set? So then it actually means that fg is analytic in an open set which contains. Okay, so therefore if I have a function f from say S or some C to C, and suppose you have a subset S subset of C, some set, I am not talking about it is an open set. Now if I say that my function is analytic on S, that means what I am doing is that, so I am saying that consider an open set, D is an open subset of C and S is contained in D, and then I am saying that my function is analytic in that open set, because I already discussed what is the meaning of analytic on an open set. Okay, so if I talk about analyticity on some set S, that means I am saying that, okay, you have an open set which contains your set S, and I am talking about the analyticity of F on that open set. So that's how you mean the analytic on a set S. Okay, now couple of results regarding analyticity. Okay, so first theorem, well, this is actually follows from the definitions. What I have written, that if Fz is analytic in an open set, then Fz is differentiable in D. Yes, Fz is analytic in an open set means what? My functions by definition, or you can say that it is analytic at each point. Well, in that sense, or if since it's an open set, of course, the meaning of analyticity means I am talking about differentiability at each point. So therefore, it follows from the definition. So you can think about as a like theorem. You can say that. So if I have an analytic on an open set or analyticity on an open set, it will implies the differentiability in D. But see, there is a note. This is very important. It says that converse of the above theorem is not true. That means analyticity implies the differentiability. But what about the vice versa? Is the differentiability implies analyticity? Answer is no, because these functions, like as these functions, g of z is equal to mod z square. So therefore, even though my function is differentiable at a point 0, but my function is not analytic at a point 0. Okay, so this is origin. So at the origin, my function is differentiable, perfectly all right. But to talk about the analyticity at the origin, that means I need a open neighborhood around that origin, and I want that my function should be differentiable at each point. But I know this function is differentiable only at the origin and nowhere it is differentiable. So therefore, this function is not analytic. So therefore, analyticity implies differentiability, but converse is not true. So there is a necessary conditions, of course, like the necessary conditions for differentiability. Now you can also guess what sort of necessary conditions you will have. Okay, so like what is the statement of the theorem? Let Fz be analytic in an open set D of C. Okay, then I am saying that Fz satisfies Cauchy-Riemann equations at each point. Okay, so if you go back the definitions, I am saying yes. Okay, right. Okay, so look, let F from D subset of C, Z naught is a point, then analytic at a point I have defined, then I am saying that analytic in D, that means F is analytic at each point. Okay, so therefore you just remember the definitions. Now look at this theorem. Now if I assume that my function is analytic on an open set, like that means my function is differentiable at each point, which actually this is a theorem. But what is the necessary conditions for differentiability? If I have a function which is differentiable, it should satisfy Cauchy-Riemann equations. And since analyticity implies differentiability at each point, so therefore it is expected that Cauchy-Riemann equations should be satisfied at each point. And that is the necessary conditions for analyticity. So therefore, let Fz be an analytic functions in an open set D subset of C, then Fz satisfies Cauchy-Riemann equations at each point of D. So you do not need any proof. This is straightforward, right? So you know the necessary conditions for differentiability at a point, which implies that if I write my functions f of the form u plus ib and u and v should satisfy Cauchy-Riemann equations. Now analyticity implies what? It is differentiable at each point. So therefore it is expected u and v should satisfy Cauchy-Riemann equations at each point. So that's the necessary conditions. Now you can ask like, okay, like I have a sufficient conditions for differentiability. Now can I have a sufficient conditions for analyticity? And of course, the way I have given the definitions, that analyticity, that means it should be differentiable at each point. So therefore sufficient conditions says that what is the sufficient conditions for differentiability? That means all the first order partial derivative exist. So suppose f is of the form u plus iv, all the first order partial derivatives of u and v exist, they are continuous and they are satisfying Cauchy-Riemann equations. If they are satisfying Cauchy-Riemann equation at a point, then my function is differentiable at that point. Now if the Cauchy-Riemann equation satisfies at each point, then I am by sufficient condition for differentiability, I am saying that my function is differentiable at each point, and then by the definition of analyticity, my function is analytic. So that's exactly the sufficient conditions you can expect. So sufficient conditions for analyticity: suppose f is of the form u plus iv, be defined in an open set D if the first order partial derivatives of u and v exist, they are continuous and satisfies Cauchy-Riemann equations, but this is very important, at all points. Okay, and if this is the case, then by sufficient condition for differentiability, I am saying that my function is completely differentiable at each point of D, and then it is the definitions that definition that my function is actually analytic on D. Okay, so now, earlier I will have necessary and sufficient conditions for differentiability. Now I already have a necessary and sufficient conditions for analyticity. So the difference is that the differentiability I can talk about at a point. However, the analyticity, whenever I am talking about the analyticity of my functions f, that means I am talking about analyticity on an open set or on a set. So therefore, whatever sufficient and necessary conditions for the differentiability you will have, it should have the similar way, but this time I will have to be more cautious, because it has to be like it should satisfy at all points. That is very important. Okay, so this is necessary and sufficient conditions for analyticity. It is straightforward proof, so it is actually follows from necessary and sufficient conditions from differentiability. Okay, so this is the gist. Actually, I have just kind of combined like the way I have talked about differentiability, complex differentiability. So I am saying that in case of analytic functions in an open set D, the previous results become necessary and sufficient conditions. So in other words, what it says, if my functions f of the form u plus iv and it is an analytic in an open set D subset of C if and only if all the first order partial derivative u and v exist, they continuous and satisfy Cauchy-Riemann equations at all points of D. So this is the kind of, you can think about as a theorem, necessary and sufficient conditions for a functions f which is analytic in an open set D subset of C. So a functions f which is of the form u plus iv which is analytic in an open set D subset of C if and only if all the first order partial derivatives of u and v exist, they are continuous and they are satisfying Cauchy-Riemann equations at each point of D. If that is the case, then I am saying that my function is analytic, and if f is analytic, this is automatically true. Okay, so couple of more results. Okay, so this is like, you can think about as a differentiability. So that is like, for example, if I have two differentiable functions f and g, so what can I say about the f plus g? What can I say about the f minus g? What can I say about the f times g? So this kind of results you know in case of differentiability, but in case of analyticity, similar sort of properties also true. So it's, in other words, it says that if I have two functions f and g which are analytic in an open set D subset of C, then the functions f plus g, f minus g, f times g, these are all analytic functions if g is non-zero in an open set D, that means z belongs to D, g of z is non-zero, then this f divided by g makes sense, and I can also say that this is also analytic. So these are algebra of analytic functions. Again, I am not proving it. This is like if I have two analytic functions, what can I talk about the compositions, like the chain rule, differentiability, you know, right? If I have a functions f and g, and suppose f composition g makes sense, and suppose both functions f and g are differentiable, then I can talk about f composition g which is also differentiable. Similarly, same kind of questions you can ask. Okay, if I have two analytic functions and suppose composition makes sense, can I have the analyticity of the composition function? Answer is yes. Okay, so it says that if f is analytic in an open set D and g is analytic in an open set containing fd, that means of course composition makes sense, so therefore g is analytic in an open set containing, because f of d need not be open, right? So that means f of d should be a set. So that means if I want to talk about analyticity on the set f of d, that means I need an open set which contains my f of d and my g is analytic. So that's what the statement I have written. So if f is analytic in an open set D, perfectly alright, you know the notions, then g is analytic on an open set containing f of d, because f of d is a set. So analyticity means there is an open set containing f of d and g is analytic there. Then the composition functions g composed f which is g of fz which is also analytic, you can prove it. So it's just straightforward. Maybe you can take it as an exercise and you can prove it, because what you have to do, you have to just check that my function is differentiable at each point or not. Okay, so you just use the like definitions of differentiability, or you have a necessary sufficient conditions because your functions f and g are differentiable, and try to show that it is differentiable at each point, and then by the definition of analyticity my function is analytic. So these are the theorems, you can take it as an exercise and do at your home. Okay, this is just follows from the principal definitions of differentiability or necessary sufficient conditions for differentiability. Write it clearly. If you understand the earlier theorems very clearly, then you will be able to prove this theorem. Take it as an exercise and prove it. Okay, maybe this is one of the theorem which is more interesting, and that maybe later on I will prove it. What it says is that if I have analytic functions on an open set D subset of C, then what I am concluding? I am concluding is that then the derivatives of all orders f exist and they are also analytic. That is, the f and z n exist for all n, and that is also analytic. Now this is a very powerful property. That kind of property you do not have if I just talk about say differentiability. That means, like for example, if I have a real valued functions of real variable, you know, or you can construct. Suppose a function which is one times differentiable but not twice differentiable. That means f prime exists but f double prime doesn't exist. Or maybe my functions f is n times differentiable but not n plus 1 times differentiable. Similarly, for if I have a complex valued functions of complex variable, then you can construct a function is one time differentiable at a point but which is not twice differentiable. Similarly, by functions it is n times differentiable but not n plus 1 times differentiable. So therefore, what I am trying to say is that, so existence of once differentiability or twice differentiability will not allow you to talk about the existence of the next differentiability. Like if I want to talk about first differentiability or second differentiability, it will not automatic that your functions will also be third times differentiable or fourth times differentiable. You can have explicit examples. However, if I have analytic functions on an open set, then my conclusion is that all the derivatives of f exist. Not only that, they are also analytic. Now that is why the rigidity of analyticity came into the picture. Because, see, as I said, so the two concept differentiability and analyticity is a very rigid property. So therefore, I should expect something nice should be come out from the analytic function, and this is one of the theorem you can think about. It is very powerful theorem and very strong theorem. If I have a analytic functions in an open set D, then my conclusion is that all other derivatives of my functions f exist. This itself is very powerful. Not only that, they are also analytic. So this is a very powerful theorem. This kind of phenomenon is not true if I just want to talk about differentiability. No, it is not the case, because analyticity, as I said, it's a very rigid property. So therefore, if I have analytic functions, therefore it has to give you something nice, and this is the one of the nice behavior of analytic functions. If I have analytic functions, then all other derivatives of f exist and they are also analytic. In other words, fnz exist for all z in D and they are also analytic. So that maybe there are many ways you can prove it, but maybe when I will talk about what is called power series or Cauchy's integral formula, there I'll tell you, because to prove that one, once I'll talk about the Cauchy's integral formula, from there it will automatically follows that if I have analytic functions, then all nth order derivative exists and they are also analytic. So for the time being, you just assume or you just kind of read the statement that how powerful this theorem is, but the proof, when I will talk about Cauchy's integral formula, using Cauchy's integral formula, I will be able to prove that theorem. And also later on, when I will talk about power series expansion, there also you can you will be able to prove this theorem. Okay. This is another theorem like results of analyticity. Like in real case, you know, if I have a like say differentiable functions and suppose derivative is 0, then is the function is constant, this kind of things. So now suppose I am just writing as a theorem, suppose f is analytic in an open and connected set, and suppose derivative is 0 everywhere in D, then automatic I am saying that my function is constant. There also you can prove it, okay, but you should be always careful that this D should be open and connected. That means I need a function defined on a domain, right? Domain means open connected set. So connected is very important, okay, and you can easily prove it. Why? Because you have a functions f, right, which is D subset of C, which is open and connected, right? Then I am saying that if the derivative is 0, then my function is constant. Okay, you just write it. Now f you can write it as of the form u plus iv, right, that you know. Now what is your hypothesis? It is analytic in an open and connected set. That means my function is differentiable at each point, right? And since my function is differentiable at each point and you know the derivative, right? So suppose take a point z0 in D, right? And what is the derivative at the point z0? If z0 is say x0 comma y0, or say this is same as x0 plus iy0, whatever it is, what doesn't matter which notation you are using, okay, then what is the derivative of f at z0? Then you can say that I already explained. So this derivative you nothing but you can say that ux at the point x0 comma y0 plus I times vx, right? If you remember, go back, you will have these expressions, okay. And this is true for all z0. Whatever point z0 I can take, since my function is analytic, that means my function is differentiable, and the derivative I can explicitly write ux plus I times vx. But what is your hypothesis? A prime of z0 is 0, because a prime of z is 0 for all z, so therefore a prime z0 is 0. So therefore this will implies that by hypothesis 0 is equal to ux at the point x0 comma y0 plus I times vx at the point x0 comma y0, right? Then what will implies? That means since this is real, so therefore ux at the point x0 comma y0 is 0, same as vx at the point x0 comma y0. So that means ux and vx, they are 0 at the point x0 comma y0. But you have something more. What is that? Since it is complex differentiable, so therefore u and v satisfies Cauchy-Riemann equations. So this will automatically implies your uy at the point x0 y0 is equal to 0 and vy at the point x0 comma y0, that is also 0, using Cauchy-Riemann equations. So therefore you have all the first order partial derivatives of u and v at the point x0 y0 is 0, And what is x naught, y naught? That means it is a point z naught, and it is true for all point, right? So therefore, actually you can conclude that ux, uy, vx, vy, they are all 0 functions over the domain D, which is open and connected. Now, if I have a functions u, what sort of functions u? U is a map from R2 to R, right? So u is defined from D subset of R2 to R. And all the partial derivatives of u with respect to x variable and y variable, they are 0, and my domain D is connected, open and connected. So therefore, u is free from x, u is free from y, v is free from x, v is free from y. So therefore, u is a constant, v is a constant, and hence f is a constant. Okay, is it clear? So therefore, so first you have the analyticity, you just write u plus iv. Using the hypothesis, you conclude that ux and uy is 0. So from the differentiability, you have ux and vx is 0. Then using Cauchy-Riemann equations, you can say that ux is 0 and uy is 0 at that point x naught, y naught. Now since it is analytic at each point, so therefore this ux and uy is 0 at each point on my domain. Now u is a function from open connected set D subset of R2 to R, and u is partial derivative of u with respect to x variable at any point is 0, and similarly partial derivative of u with respect to y variable, that is also 0. So therefore, using the kind of analysis or results from the real analysis, you can say that u is free from x and u is free from y. So therefore, u is a constant. Similar way, you can say that v is also free from x, v is also free from y, so v is constant. Since u is constant, v is constant, so therefore it will imply that f is constant. Okay, but you have to be really careful that to talk about that if I have a functions u from some domain D subset of R2 to R, and if my function is nice functions with the fact that ux and uy are 0 at each point, and if my domain is open and connected, this is very important, open connected, then only I can say that u is free from x and u is free from y, and in other words u is constant. So that's the only theorem from the real analysis I am using. So you just do the part for u and v separately and conclude that u and v are constant, and then you have f is constant. So that's how the proof of this theorem. Okay, so now many nice results you can have the analyticity. Okay, so this very nice result you can have it. So for example, there are 9 exercises. You can think about this as an exercise, nothing else. Okay, so this is very nice. So maybe you can expect this kind of problem will be there in your exam. Okay, so what I am saying is that, okay, suppose you have a function f which is u plus iv, suppose it is analytic in a domain. Now you see I am kind of giving this problem, and I am assuming that my function is defined on a domain. Domain means it is open and connected, this is automatic. Okay, then what I am saying is that if one of the following conditions hold in the domain, then my function has to be constant. Okay, so now I hope the problem is clear. So I am starting with a functions f which is of the form u plus iv, which is analytic in an open connected set D subset of C. That's first kind of hypothesis. Then I am saying that if any one of the following conditions out of 9 conditions, if this is true, then you do not have any other options unless your function is constant. For example, look at the first one. If my function is analytic in an open connected set, and if the derivative is 0, then my function is constant. Just now I have explained in my last slides. So if f is analytic in a domain and if derivative is 0, then f is constant. So how to do that? So you just say that f is of the form u plus iv, then just since my function is analytic, it is differentiable, write the expression of the derivative using the hypothesis f prime of z is 0. From there you can conclude that your u and v, or you can first conclude that your u x is 0 for each point in D, u y is 0 for each point in D. Since D is open connected, u is free from x, u is free from y, hence u is constant, and similarly you can do that v is constant, so therefore f is constant. So therefore first one I am done. Now let me just check the second one. What is the second one? It says that, okay, I have a function f which is u plus iv, which is analytic, with the fact that suppose u is constant, then I need to conclude that my functions f has to be constant. Okay, now f is equal to u plus iv, right? And what is your given? That f is analytic in an open set or in a domain D subset of C with the fact that u is constant. Say u is some C1. Then I have to show that f is constant, and that you can easily do that. Why? Because you see f is analytic, right? So f is analytic means what? That means your functions u and v, that first order partial derivative should exist and they are satisfying Cauchy-Riemann equations, right? That's the necessary conditions for differentiability. So now f is equal to u plus iv, where u is equal to constant. So now if I take the partial derivative with respect to x variable, what it will give? 0. Similarly, if I take the partial derivative with respect to y variable, that is also 0, because the necessary conditions. Now f is differentiable, it's satisfying Cauchy-Riemann equation, so therefore it will implies ux is equal to vy and ui is equal to minus vx. So therefore ux ui 0 implies vx vy also 0, and this is true for all point, right, because u is constant in the full domain. So therefore ux and ui is 0 for each point on the domain. Then using Cauchy-Riemann equation, because my function is analytic and hence differentiable and hence necessary conditions for differentiability implies that ux is equal to vy and ui is equal to minus vx. So therefore ux ui 0, which will implies your vy is 0 and vx is 0 for each point in D, and D is open connected. So therefore if vy is 0 and vx is 0 and it is true for each point, so therefore v is free from y and v is free from x, so therefore v is constant. So v is C2. Now you already have u is constant, now you prove that v is constant, so therefore u plus iv, that is constant, so therefore hence that f is constant. Similarly, now you can guess how to prove 3. So you have analytic functions f is equal to u plus iv where v is constant, okay. Now since v is constant, again just repeat the same process, okay. So here f is equal to u plus iv, v is constant, say C2, f is analytic in D, which is open and connected. Now analyticity implies differentiability. Necessary conditions for differentiability implies that its partial derivatives of u and v exist and they satisfy Cauchy-Riemann equations. Now come back here, v is constant, so therefore vx is 0, vy is 0, perfectly alright. Now again using CR equations, you can say that ux is 0 and ui is 0. Now ux is 0, ui is 0 for each point in D, for all point in D, because v is constant, because vx and vy is 0 at each point in D, which will implies by using CR equations and necessary conditions for differentiability implies that ux is 0 and ui is 0 at each point in D. So therefore since D is open connected, so therefore u is free from x, u is free from y, so this will implies u is constant. So I already have a v is constant, then I am proving that u is constant, so therefore my function's f is constant, okay. Now what about 4? If fz is real value, now you can guess, right, what is fz? Fz is real value means what? If I can write f is equal to u plus iv, right, and f is real value, what does it mean? That means your imaginary part is 0, that means v is equal to 0, and v is equal to 0 means what? V is a constant function, right, 0 functions, and you already proved in 3 that if v is constant, my function f has to be constant. So therefore if I have an analytic functions which is taking purely real valued, then this functions has to be constant. That means you cannot have a non-constant analytic functions in an open connected set D which is taking purely real valued, okay. Similarly this also you can do that, fz is taking purely imaginary value, that means you cannot have a non-constant analytic functions f on an open connected set or on a domain D which is taking purely imaginary value. Again the same argument, so f is of the form u plus iv and I am saying that fz is taking purely imaginary value, that means what can I conclude about u? That means u has to be 0, and since u is 0, that means u is constant, and if u is constant, you already proved into that f has to be constant, so therefore f is constant. So what about 6? That is also another interesting fact. If modulus of fz is constant, then you have to show that your f is constant. That also you can do that, okay? Because you see, what I will have, f is equal to u plus iv, I will have, and it is analytic in an open set, and what is given is that modulus of f is constant. Now what is modulus of f here? So modulus of f, that means modulus of u plus iv, that is constant. Now mod f is constant means what? You can say that mod f square, so you can say that modulus of f is say c, okay, and say c sum is positive, okay. Then modulus of f square, that means c square, that is also constant. Now what is modulus of f square? So that means you can say that this is u square plus b square, okay. So and this is constant, c square, this is positive, suppose this is constant, and I have to conclude that f is constant, that means I have to prove that u and v are constant, then I am done. Now here you have to do some little algebra. Now you see u square plus v square is constant, so what I will do, since my functions f is equal to u plus iv and my function is analytic, that means it is differentiable, that means all first order partial derivative exist and they are satisfying Cauchy-Riemann equations. So what I will do first you take the partial derivative of this equation with respect to x variable, so that means this is 0, u times ux plus v times vx, okay. Again do the partial derivative with respect to y variable, so therefore you can say that 0, which is u times ui plus v times vy, okay. Now this is two equations you will have, but u and v satisfying Cauchy-Riemann equation, that means ux is equal to vy and uy is equal to minus vx. So what you will do, you just replace this equation, so this one you just replace it, so 0 is equal to uy is equal to minus vx and v is equal to vy means ux. Now you have 1 and you have 2. So you do some algebra. What I will do, so I will hit 1 by some constant, so that so what I will do, so I will hit, yes, I will hit 1 times u and 2 times v. Yes, what it will give, let's see. So 1 times u means u square times ux plus u v vx, right, minus, you see, 2 times I am v, so that means here u v times vx plus v square ux, right, this is 0, right. 1 times u plus 2 times v, I am just doing the algebra. What it will implies, this will get cancelled. What it turns out that u square plus v square times ux, this is 0, right. But what is u square plus v square? It is c square, it is positive, ux is 0. What it implies? Ux is 0, right. So therefore, using this kind of algebra, you actually prove that ux is 0 at each point. So that means u is free from x, right. Now, but ux is equal to vy by Cauchy-Riemann equations, there also you can say that v is free from, or vy is 0. So therefore, u is free from x, v is free from y. So in the same way, you can show that uy is also, do the same algebra, right. Maybe 1 times v, or using the Cauchy-Riemann equations here, you can do the same. So using this algebra, I am saying that ux is 0, that means u is free from x. Using Cauchy-Riemann equations, I am saying that vy is 0, that means v is free from y. Do the same algebra, you can say that u is free from y and v is free from x. So therefore, u is free from x and y, therefore u is constant, v is free from x and y, therefore v is constant, and therefore f is constant. Okay, that's how you have to prove it. So this is the only one, you need some algebra, and rest of them this is also you can do. So to take it as an exercise, so what is this one? F of z bar, that is very easy. So what is f of z bar? This is, if f is u plus iv, this is what? U minus iv, right? F of z bar is u minus iv. Now you have a f is analytic and f bar is analytic. Therefore, f plus f bar, what is that? If I just add it, this is u plus iv, and what is this? This is u minus iv, right? Now this will get cancelled. So what you will have? You will have exactly 2 times u. Now f is analytic, f bar is analytic. So therefore, sum of 2 analytic functions is analytic functions. So therefore, left hand side is an analytic functions, right? But what is that analytic functions taking value? 2 times u, and what is that? This is purely real valued. So you have an analytic functions which is taking purely real valued, but what it says, if I have an analytic function which is taking purely real valued, it has to be constant. That means you can easily say that f plus f bar is constant. Similarly, you can say that f minus f bar, that is also analytic functions, because f is analytic, f bar is analytic. Substructures in analytic functions, they are taking purely imaginary value, so this is also constant. If I add it, that will implies f is constant. So this is very nice, you should just complete it. So this I have done it. Similarly, you can prove this and this. Okay. So that's like, if I have an analytic function, these are the kind of couple of exercises I have given. You can easily just use the differentiability, definition of differentiability, Cauchy-Riemann equations, play with do some algebra, then you will be able to prove those kind of exercises. There are many, I am just listed very few. You just do in your home. So only two are remaining, 7 and 8, you should complete it. Okay. So I think that's all from this lecture. So I have talked about analytic functions, and then I talked about the necessary and sufficient conditions for analyticity, and a couple of nice exercises. So I have almost done all the exercises, but 2 or maybe 7 and 8 I have left as not 8, 7 and 9 I think, yeah, 7 and 9 you just complete it. Okay. So these are very few, but there are many, but somehow you have to play with necessary and sufficient conditions for analyticity, differentiability, Cauchy-Riemann equations, and do some algebra. So but at the end of the day, these are very nice exercises, you should try to complete it. I think that's all from my side for this lecture. Next lecture I will introduce the notions of what is called harmonic functions, and we will see there is a connections between analyticity and harmonicity. I think I should stop here. Thank you.